Hi, I'm Abby, and this is for Project 1. So the goal is to use Taylor's theorem with the Lagrange remainder to determine the degree n required to get an error of less than 0.0001 for the function ln of 1 plus x centered at 0, and the point we're evaluating at is 0.05. So the first thing we need to do is find the derivatives so we can look for a pattern. So I found the first 10 derivatives just to be safe. So you can see my derivatives here, and we see a pattern starting to develop where every other derivative is a negative number and the numerators are going up by a factorial. So with that information, I came up with this formula for the nth derivative, looking at the pattern, and it's between 0 and 0.5, and so you can see here I check it just to be safe, so that I can show how it works and stuff. So I just randomly chose the sixth derivative, so we'd plug in 6 minus 1, which is 5, and so if negative 1 is being raised to the power of 5, it's going to be a negative number, so we get a negative. Then we need the 6 minus, or the n minus 1 factorial. We need that to walk down, so we have 5 times 4 times 3 times 2 times 1. We get this 120 on the top, and then the denominator is 1 plus x to the sixth. So here's what I get, and let's see if that matches the derivative I found up here for n equals 6, and it does. So that makes me feel good that this formula for the nth derivative works. So that's good, but when we look at the Lagrange remainder, which is what we need to use, we actually see that we need it for the nth plus 1 derivative. So what we do is we actually need to plug in n plus 1 for everywhere that there was an n in the above equation that we came up with. So this is going to simplify out to this right here, because it'll be n plus 1 minus 1, right? So we can just have n, same thing here, n factorial, and on the denominator we have n plus 1. So that's good because now we have the function for the nth plus 1th derivative. And now we need to bound this. So if we look over at Desmos, here is the function we're looking at, and I have graphed the first 4 derivatives right here. So when we look at this between 0 and 0.5, we can see that they're all decreasing to an asymptote at the 0 on the horizontal, right? So they're all decreasing to this point. So the magnitude is going to be larger at 0 for all of these derivatives than at 0.5, because that's the point we're evaluating at. So in this range between 0 and 0.5, our magnitude is larger when it's at 0. So we can also see that if we do it here on paper, we can plug 0 in for both of these. And on the bottom here, we'd have 1 plus 0. So we have a smaller number on this denominator than this 1 plus 0.5. And when we're dividing by a smaller number, we're going to get a larger number. So that means that our maximum value for our nth plus 1 derivative has to be when it is at 0, right? So that means that we can plug 0 into our equation, since that is the maximum value we could get. And we see here on the denominator, we basically get 1 raised to some power. So we can just leave that as 1 and get rid of the denominator, because 1 raised to any power is 1. So it simplifies to this. This is our maximum formula for the nth plus 1 derivative. So we are able to plug this in to the nth plus 1 derivative on the Lagrange remainder formula so that we can find n. So here's what it looks like. We have the n plus 1 factorial on the bottom. That's part of the Lagrange remainder. And then we have x minus 0, since it's the center is at 0. And so for our x, we're going to put in 0.5, since that's what we're evaluating at. So I use Desmos over here to help me solve this so that I don't have to, plug in a bunch of numbers and solve it by hand. So I just have this scroller here. I plugged in 0.5 to this equation, and I'm just going to scroll it. Remember, I need this output, my c value, to be less than 0.0001, right? So we need to go up in degrees a bit. So let's check. We're at 7, right? It's still too big. We need this to be a 1. Let's keep going. We're at 8. Still too big. We need this to be a 1. Let's go to n equals 9. And that's perfect. It's right below the 0.0001 that we're looking for. 8 was too small, and 9 is just under. So that means that in order to get an error of less than this 0.001, we have to have a degree of 9. So I wrote out the whole Taylor polynomial here. That's what these numbers were from. Up here, I evaluated all of our derivatives at 0 to get the numerators that will go into our Taylor polynomial. Down here, this is the function for the table, or the equation for the Taylor polynomial, and we're going out to the 9th degree, since that's what we found in part A that we wanted. And so this is what our Taylor polynomial will look like when it's simplified. And now we want to use the Lagrange remainder with our n equals 9 still to find what the error, the maximum error would be at 0.2 instead of 0.5. So since we already did all the hard work in the first part, all we need to do is change this 0.5 to 0.2 over here and keep n at 9, because the output that it gives us, the c value, is going to be the maximum error that we can get. So we get this output of 1.024 times 10 to the negative 8. We're just worried about the magnitude. So basically, this is the largest possible error we can get when we use a 9th degree Taylor polynomial in the Lagrange remainder for the function ln of 1 plus x when we're evaluating at 0.2. So thank you very much, and let me know if you have any questions. Have a good day.